sorry. So good morning, everyone. How are all of you today? Fine and pretty good and tired. Okay, well, you know. So, of course, what we're going to be doing is we're going to start now Unit 2. This is where we get into more nitty-gritty actual statistics work, what we normally think of as statistics, because so far, all you've covered are things like standard deviation, mean, median, mode, how to display the data and all that stuff, and that's important, but that's kind of foundational to something that's more critical here, and that's kind of the heart and soul of stats. Because as I've hinted at, so much of stats is we have this weird thing going on. Is this thing the new standard, or is it just weird for random reasons? You plant a bunch of flowers, or you plant a crop, you use a new fertilizer, it grows really well. Was that a weird crop seed? Was this just random fluctuation? Or is this fertilizer really that good? So much of stats is about untangling between, you see something weird, is this random or is this something genuinely new? And so we're going to be building that foundation of understanding in this class with the normal distribution. So, how many of you have heard of the normal distribution before? Yeah? So tell me more. What do you mean? What do you know about it?
Your median and your mean probably in the center, and then everything else is spread out. And like there's certain points that like the distributive, like percentiles almost. Okay.
No, I like what you hear. So there's a lot of data in the middle, and then it's kind of spread out. And you know what shape it generally forms, Michael? It's the bell curve, right? So Priyanka's actually is pointing out right on it, right? It's this bell curve, Michael, right? Is absolutely right. The normal distribution.
Okay, so it's your ideal of what you want.
So I should actually mention it's a symmetric bell curve. It's not necessarily an ideal distribution, but it is our default assumption. And you can see that here. So in order to give us some good grounding as to why we use the normal distribution so much, I want to illustrate to you empirically, it comes up in lots of different areas. So for example, we have IQ, this is the green one right here. IQ scores follow a normal distribution. It's not perfect, but you can see I don't know if you can see it. This line, that is the normal distribution. It follows it really carefully. It follows it really closely. We have this is height of ultra runners right here. Again, a lot of the observations in the middle, and then it kind of tails off in bell shape. This is time to stop line, which is the Department of Transportation. I believe uses it's time, like people are driving, they see the light turn red, how long does it take them to stop? So this is measured in seconds. You get an idea of the delay. And it kind of follows it. It's not perfect, right? Sometimes messy, but it's still pretty good. Here's the pre-tax operating margin for auto manufacturers. Same kind of story. Looks like it's a normal distribution. Here we have a price distribution of houses by the number of bedrooms they have. Same kind of story. It gets a little weird here when we do 4 and 5 bedrooms, but the sample size is so small it's not really that crazy. But you see it kind of here, this general shape. So that shape of a lot of observations and then split out into a bell curve is something that empirically has a lot of support. And we are going to generally assume that things follow a normal distribution. And it's not some random assumption too, as you'll see, it comes up also from something called the central limit theorem, that it also follows a normal distribution. So it's a pretty important idea. So important that we're going to play with it a little bit. It has kind of 2 ways to think about it. Before we get into it. When I say symmetric, what do you think I mean? What does that mean? Yeah?
Exactly.
Exactly.
they are mirror images of one another, right? In other words, the mean equals the median, right? Because it's noted, right, same amount above and below the mean, so the mean is the same thing as the median. Perfect bell curves, as you can see empirically, perfect bell curves usually don't happen. And so we have terminology to describe when they are imperfect. Skew and kurtosis. Skew is kind of a more common word. Has anyone ever heard that before? Skewed data. Yeah, I see some people nodding their heads so slightly. I'm learning names. The name again is.
Okay. So you're right. It's about outliers, but we don't want to say because there's an outlier it's skewed. We're trying to describe the whole data set. So we might say that the data set is skewed right or it's skewed left. But in fact, we sometimes call this a positive or right skew,
Or a negative or left skew. Positive right, because obviously on a number line, as you go to the right, you get larger numbers. In the positive territory, negative or left, because as you go to the left, you go into the, negative x. So you can easily spill past 0 and go to the negative section. But it is exactly as it sounds. Positive skew might look like that. Let me make this even more extreme. It looks kind of the same, it looks like a standard normal distribution on the left-hand side, but on the right-hand side, there's this very long tail outward. Left is exactly the opposite, a long tail outward to the left, but on the right-hand side, it looks normal. An example of a distribution that would look like that has a positive skew, can anyone give me an example? A variable with a positive skew. Yeah. Salaries, perfect. Classic example. Why? Yes, but it's going to be true generally even, right, across the board, right? There's going to be an average here, and then there's going to be some a small number of people that have very, very high values, right? And that's that outlier issue that everyone was talking about. Except we're not saying that there's one or two outliers, there's enough to actually see a really clear skew. And there are more outliers on the right than the left, otherwise they don't just look flatter. Everyone good so far? Well, they're really outliers, right? There's a whole bunch of them. What would be something that has a left skew? Yeah?
I feel like maybe height of basketball players, because I feel like more of them would tend to be on the one side, and then you'd have a few that are a little bit shorter on the other side.
So you're saying that there's going to be a few very, very tall ones. Because remember, the average is going to be wherever we want it to be. And then there are some super short, there's like some midgets on the field. I don't really follow basketball. I don't know if that's the case. So there's some very, very unusually low values. Think about like where the central tendency is. And then think about, are there people that are disproportionately way to one side or the other?
So what I was thinking in terms of like, from like 7 to like 5.5.
I think he's saying that the majority of basketball players are taller. So
tall.
Toward the end, it was 6 foot to 7 foot. So the majority of them are in between there.
Right, but we don't want to be distracted by like, because it's over here, that means like we push it over and like this is the default middle. Like we're saying whatever the average height is, you know, well, technically wherever like the median is, might be right about here. So you have to think in context of what you're looking at. You know, like for example, what do you think, like, I have some data from grades from like a 2014. What do you think the most common grade I gave was?
Probably a B.
A B is actually correct. So the modal grade was a B. In fact, we can actually pull up some data, and I can show you what I mean, because I have data. This is the grade distribution. So you see that A, of course, if we translate A onto a 4.0 scale, how much is the A worth for your GPA? 4, right? It's worth 4. So I'm going to put the A over here on the right. And then B's are, of course, 3s, C's are 2s, D's are 1s, and F's are 0. That's a little tilted. There we go. Draw a straight line. In other words, right, rather than using this because A is on the left, even though A is the highest number, and F is on the right, even though F is the lowest number, I flip it to reflect that. You see, this follows a left skewed distribution. Pretty clear. So that's kind of why I'm thinking. That's why I'm not sure about the basketball players. I can see there's a lot of variables, right? You know, wherever you put the height at, but I don't know if in the context of, say, a B, or in the context of the average or the typical basketball player height, are there some even taller ones that are usually high, or are there some like really outlier short ones? I don't know. I'll have to look at the data. So, what do you think, by the way, based on this data right here, by the way, there's 140 observations, 140 grades. What do you think the median is? The median grade, the middle grade. So I told you the most common one, the mode, is B, right? Obviously it's the highest one. But what is the middle grade? B. How do you know, Laura?
Because you just said one symmetrical filter, the median will be the low. I mean, the median.
It'd be like roughly 50 and 50. It's just a matter of where the mean is pushed. So the median is always going to be that peak. So it's going to be a P.
The mode. I'm sorry, the median, right? The median doesn't have to be a P. Like, if I gave 51 A's and 38 B's, then the mode would be A, and the median would still be B. The median's B. Right? So there's 140 observations. There's 140 grades. That means the median grade is between the 70th and the 71st observation. So if we count 70 from the left, that's 38. I'm going to get the 70th somewhere in here. If we count 70th from the right, or 70th from the left, then 8 plus 6, that's 14, plus 37, that's 51. 51 is still not 70, so I keep counting and it'll be somewhere in here. Right? The median is 3. The median is 3. And if you do the math, 8 zeros, so 0 times 8, plus 1 times 6, plus 2 times 37, plus 3 times 51, plus 4 times 38, and then add all those together, and then divide by 140, that gives you the mean, which is 2.75. In other words, when we skew things, mean and median are no longer the same. In a negative skew, median is greater than mean. In a positive skew, median is less than mean. So you see things like we have data on, like, say, average student loan debt. That's a much higher number than median student loan debt.
because some outliers, people who are going to law school, people who are going to become doctors, they get very easily 6 figures of debt, and those small numbers of very high values drive the average up. Okay. Those outliers we talked about last year.
Any questions about skew? Yeah.
Can you let me know how you got median is equal to 3? Are you talking about the grade that's assigned to 3 or?
No, I was 3 is a B because that's one. So I counted. There was 140 observations, so I counted. Trying to count to 70, and I get in here.
Right, no, right, but then how'd you get median is 2.75?
Oh, so there are 8 zeros, there are 6 1s, 37 2s, 51 3s, 38 4s, right? And so if you were to add all those values up, it would be the same thing as 8 times 0 plus 6 times 1 plus 37 times 2 plus 51 times 3 plus 38 times 4. And then when you add all that up, you get a total of 385. And then you take 385 divided by 140, you got 2.75. Any questions?
Kurtosis.
So skew is a measure of symmetry. Kurtosis is a measure of peakness. That. Positive is a sharp peak. The middle is sharp, it's concentrated. It looks kind of like that. Or a lot of the observations are clumped near the mean. Standard deviation is pretty low. A negative means a flat peak. Well, a lot of the observations are spread out, and standard deviation is relatively high.
More of the variance is due to extreme observations. For positive, because
it's just due to like these really random ones that are just really out here. That's where most of the variance comes from, because a very small amount of the standard deviation, a small amount is due to this. Well, here a lot of the variance is due to just like all the observations in general, right? The outliers aren't really throwing things off.
So,
there's no skew, and the kurtosis is 0. And then that's our reference point. A standard normal distribution no skew, kurtosis equals 0. We have a more detailed definition of a standard normal, which I might as well give to you now because I'm thinking about it. A standard normal distribution is defined as a mean of 0 and a standard deviation of 1. It will, as you will see, typically refers to something called z-scores, which we will talk about in great length as we move through this unit. So if you're not familiar with a z-score, you don't want to it'll come up. We'll talk more about it. But generally speaking, a standard normal distribution is kind of like our idealized thing we have in our mind, that perfect bell curve shape. And then when we talk about skew, it's always in reference. It's weird compared to that perfect bell curve shape. Or it's flatter compared to that perfect bell curve. It's some sort of reference point. Any other questions?
So,
yeah.
you
just as it probably will be.
Okay, and I think not low, it's just that everything
Not perfectly evenly, but more evenly. Yeah. So we know something like it's kind of flat, kind of more spread out, or it's kind of poked up a bit, it's kind of concentrated.
So you could have a very wide range and still have a flat kurtosis or a low kurtosis and big kurtosis if things are distributed more evenly.
Yeah, in fact, you will have a wider range, right? Things are kind of, I mean, assuming the range is the same, but like you could have data where like there's a similar range, but all the data points are right here. Or you can have data where it's a similar range, but all the data points are spread out. And so that would reflect different kinds of them.
We're not doing any, yeah. So, okay. Any other questions? All right. It's important we get some sort of intuition as to all the different ways data can look, just because it helps you get a little bit more comfortable working with it.
Let's imagine, to sort of apply a little bit more, let's imagine I wanted to know what the average height was of a Montgomery College student. And so I pick U5 right here and measure your height. Now, do you think I will get a good average? I picked them at random. Do you think I'll get a good average? A good representative average? You shook your head oh so slightly, no sir, or why? I don't know if you were shaking your head or you were shaking your chair, but there was some sort of back and forth movement, and I didn't really have much to go on, so I'm picking on you. Do you think that would be a good result? No, why not? Yeah, I'm only doing 5. Okay. But could it be a good result? Could it be accurate? Could it be representative of the population? Yeah, right? It depends, right? We don't really know. You want to get a larger sample, as we talked about, but larger samples are expensive, right? The more people I'm measuring, the more time consuming it is. So it's possible, we recognize it's possible that that is representative. And the question is, how likely is it? And this is where a really important idea comes up. This is called the central limit theorem. And it is the underpinning to a lot of what we're going to do in this class. It is essentially a fancy way of saying sometimes the sample mean you got is weird and unusual for a random reason. And sometimes it's not. How likely is it and how likely not? It follows a normal distribution. Sample means follow a normal distribution. Regardless of the population distribution.
The first part is pretty easy to recognize. If I take 1,000 samples, for example, a lot of them will be kind of, I'll be able to figure out if that is good or not, because I'll take 1,000 5-person samples, and those sample averages of height will follow a normal distribution. Some of them are going to be right in the middle. Most of them are going to be in the middle. Some of them might be unusually short. Some of them might be unusually tall. But it's going to follow that bell curve shape. What's neat about this is that that's true regardless of the population distribution. It doesn't matter if height is a uniform distribution, everyone has an equal chance of getting a height. It doesn't matter if the kurtosis is really, really negative and height is like kind of all over the map. Uniform distribution is just a way of saying each observation is equally likely, like the roll of a die. Each result is equally likely. It doesn't matter if the skew is super, super high. And like lots of people are really tall, and there's a few weirdos out there. I'm not weirdos is a bad way to put it. There's a few people who are unusually short. Right. I can go the other way too. That there's a lot of very short people and a few weirdos like me who are really tall, right? Whatever, right? Or that there's a lot of concentration on the mean. Right?
It doesn't matter what the population distribution looks like. The sample means will always follow a normal distribution. It will always be a perfectly normal distribution. It depends on your samples, how many samples you're pulling. But we can illustrate that idea in Excel. I'm not going to actually have you do this, but I do want you to understand it. And I found that this little Excel thing I did helps illustrate that. What you are seeing are a bunch of random samples Excel has taken. I've told Excel to take these samples. This is a little unpacking about what's going on underneath the hood. The RAND is a command to tell Excel to pull a random number, somewhere between 0 and 1. That's why there's nothing in the parentheses, because it doesn't need any import. Just pull a random number, please. I don't want to work with stuff between 0 and 1. I want to work with whole numbers. So I've told it to then take that random number and multiply it by 10. Now I have something like 5.67 or 6.29 or whatever it is. But I don't want to work with that. I want to work with whole numbers. So I tell Excel to now take that number and turn it into an integer. Does everyone follow all these steps? So the end result is I'm telling Excel to pick a random number between 0 and 9. Right. And each result is equally likely. So if you were to count the number of 9s and you count the number of 0s and you count the number of 5s, on average it will all be the same result. Good so far? Now I asked it to do this 1, 2, 3, 4, 5 times. And then I take an average of those 5 that it took. And then I do that again, and again, and again, and again, all the way up to doing it a total of 100 times. So I now have 100 sample averages, each with an average, each with a sample size of 5. Are we good so far? Right. I then tell Excel to take all these numbers and put it in a histogram. Hold on. I'm going to have to hit enter. When I hit enter, that means it's going to recalculate, which means it's going to pull entirely new random numbers. But note when I do this, this is the distribution of these averages. And if I hit F9, I can tell it to do. So it turns out that hitting F9 pauses the video. And as a result, we didn't record the rest of it. So let me just fill you in. As you can see here, when I hit enter, that would also cause a recalculation, as I mentioned, and we get a different distribution. Oops. Hit enter again. We get a different distribution. Over and over again, I can get this distribution. It's not always perfect. It's not always a normal distribution exactly, but it fits that general pattern of this, a lot of observations in the middle and then tails on the end. You never get the reverse. You're never going to get something that, it's theoretically possible, but incredibly unlikely that you're going to get a lot of values on the tail ends and nothing in the middle. This is not something you can rely on, but you can rely on it having this pattern over and over again. So that's the intuition behind the central limit theorem and what we're showing with that. Now let's move into Excel and let's apply that basic idea of normal distribution. The equation for normal distribution is incredibly complicated, and no one ever calculates it by hand. But what we can do is we can recognize that that is built into Excel. And that perfect normal distribution is something that we can then put numbers into and manipulate, and we can get information like what percent of observations are greater than 1 standard deviation from the mean, or what percent of observations have exactly this value. And that approach is built into Excel, and it is called NORM.DIST. If I type in equals NORM.DIST, you actually see I have 4 options here: NORM.DIST, NORM.INVERT, NORM.SDIST, and NORM.SINVERT. The .s in the middle just stands for standard normal deviation, a mean of 0, and a standard deviation of 1. It's a standard normal distribution, I mean. Mean of 0, a standard deviation of 1. We're going to use that later. Let's imagine I was curious about intelligence. Intelligence has IQ, as measured by IQ, has an average of 100 and a standard deviation of 15. And I'm curious what percent of people have exactly an average IQ. So I'm going to use the norm distribution function because we assume a normal distribution for IQ, and as you saw, it follows that. X is the value that you're evaluating. And one thing you can always do when you're working with this is you can hit this FX button in the upper left-hand corner, right here next to the function, and it will give you descriptions of what everything is. X is the value for which you want the distribution. I'm just going to hit it right there. It's going to think it's 0. We'll fix it later. Mean is 100, the mean of the distribution, standard deviation 15, and cumulative is a particularly important function. It is either a 1, also known as true, or a 0, also known as false. I always use 1 and zeros because it's a lot faster to type in a 1 or a 0 than to type in true and false. But you can use either. You see that it defaults to true and false in here, because I guess that's more intuitive to people. But I will typically use 1 and 0 out of habit, just so you're aware. And you can use either, it doesn't matter. What a 1 and 0 means, what cumulative means, is it will evaluate at exactly X if you type in 0, meaning it's not cumulative, or it will evaluate at X or less if you type in 1. X or less. It's always going to be or less if you type in 1. So if I type in 0, it's giving me it for X equals 0. I put in the 100 because that's the average IQ, so I'm wondering what the average, what percent of people have an average IQ, and I get about 2.66%. If I switch that over to 1, the X or less, it's 50%. It will always be 50%. Because this is a symmetric distribution, so half the observations are on one side, half the observations are on the other. If I go back to exactly evaluate and I increase the standard deviation, you'll see that, oops, I didn't cite that. Oh, there we go. You'll see it'll go down to 2%. If I increase it even more to 50, it goes down even lower because the data is being more spread out. And so as a result, there's going to be fewer observations in the middle. If I go the opposite direction and I make it say 10 or 5 or 2, you see that increases 4%, 8%, now it's 20%. And that shouldn't be surprising because the observations are pulling toward the center. So this is our kurtosis issue. It was a negative kurtosis when we made the standard deviation pretty high. It was a positive kurtosis when we made it a lot lower. Again, there's that correlation because it's that peakness of the data, that sharpness of the peak. Let's go back to 15. Now, we often talk in terms of if someone is smart or not, but it's not really clear what smart means. And yes, intelligence is very complicated. There's a lot of ways to measure what you really mean by smart and what you really mean by say average or below average, but there's clearly logically some sort of cutoff that could be implied, even if you want to consider the IQ to be narrowly defined as we're measuring intelligence. There's a cutoff where you can reasonably apply, however you want to apply it, a label of smart versus a label of not smart. And so the question is, whatever standard you apply, what percent of that population then is, by whatever standard you want, considered smart? For example, So we can do that in Excel. We'll just switch this to 1 to make that the cumulative function. And then someone in class decided that, I believe they said 120. Yeah, they had 120. They like, someone who has an IQ of more than 120 or 120 or more, we'll consider that smart. Now you see, it actually comes out to be about 90, almost 91%. And you might think, that's impossible. How can more than 90% of the population be considered smart if we're establishing some value that's greater than average? Again, remember what I said. Cumulative always looks at that value or fewer. We did not find people who had an IQ of 120 or more. We did not find the percent of population that has an IQ of 120 or more. We just found the percent of the population who has an IQ of 120 or less. 90% of the population, 91% almost, has an IQ of 120 or less. If we change this, the way we fix it is we look at the other side, right? Under the distribution, there's going to be 100% of observations. So if we found 90%, but that's exactly what we don't want, we just look at the other side, and that tells us what we do want. And that's a simple enough thing to do. We just say equals 1 minus the value, and we get about 9.12%. So by this standard, IQ of 120, 9.12% of people are smart. This is an illustration of the notes of what that cumulative function is doing. It's always looking at the x value that you put in, and then it will output this area right here, this purple area, right, or lower. If you want this area right here, this larger one, then you have to do 1 minus that. If you want it or higher, you have to do 1 minus. Subtract 1 for the higher value. What if we said 9% is too low? 9% does not hit my intuition as to what percent of the population I would call smart. In class, the student who proposed 120 as the cutoff said 9% is not what I thought I would, and that's not what I thought it should be. He was thinking that about 30% of the population should be considered smart. If we want to go that way, then we have to figure out at what value should x be such that we will get 30% right here in the square. And we could do this by like guessing and checking by putting in maybe 110, maybe 109, and maybe 105, and just trying to narrow down 106. It's not a thoughtful way to do it. There's a better way to do it. And the better way is the invert function. Here is an illustration of the invert function. Rather than putting in the x value and getting out the purple value, you put in the purple value, the area under the curve, and you get out x. So it's exactly the reverse. It's the inversion. So we can do that here. Equals norm invert. The probability we want a result of 30% or 0.3, a mean of 15, a mean of 100, a standard deviation of 15. And we get, something lower. We don't get something above average, we get something below average. Oh, you know what we did? Remember, it's always x or left, and left. It's always the left area, including the left tail. So if we want the top 30% on this side, we can't look at 0.3. We have to look at 1 minus 0.3, which is 0.7. Right? We want this larger area here. So therefore, leaving the 0.3, the 30% on the other side. So let's put in 0.7. Now you see it's 107.87. If you have if we set the standard, if we set the threshold definition of what smart is at 107.87, then at that definition, 30% of people will be smart. And we can check that by just using the equal sign, putting this in here, and indeed we get 30%. Right, you just put it back into the system, you get 30%. Now let's take an opportunity and let's reconstruct our empirical rule. I would normally ask if there are any questions here, but no one's here because I'm alone in my house. So I guess I'll just move on. Yeah. All right, so let's move on to the empirical rule. I think someone mentioned this in class, but the normal standard, the normal distribution that you know and love, that you're getting to know and love, is so standardized and so important that we have rules of thumb to figure out how much area, what percent of the observations are within 1 standard deviation of the mean, within 2 standard deviations of the mean, within 3 standard deviations of the mean. And we call this empirical rule, these 3 numbers. And they are 68% within 1 standard deviation, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. And if you can't remember that, don't worry, because I'm about to show you in Excel where it comes from. We're going to begin with our 6 numbers that we care about. The 1, the negative 1, the negative 2, the negative 3, the positive 1, the positive 2, the positive 3. These are our standard deviations. And so we are going to merge on center, highlight this area between negative 2 and positive 2 on line 3, I guess we're looking at. Merge in center, and then on line 4, row 4, between negative 3 and positive 3, merge in center. And I don't know, let's add some borders so that it's really clear what we're looking at. Ooh, and let's highlight this, and let's center that. There we go. Now, when we type in norm distribution, you actually see that there's another option, NORM.DIST distribution. This is the standard normal distribution. And you can see, as it pulls it up, has a mean of 0 and a standard deviation of 1. We're going to use that. It makes things a little easier because that means we don't have to keep putting in mean of 0, standard deviation of 1, mean of 0, standard deviation of 1. You note also that rather than saying x, it's asking for z. This comes up a lot when we're working with a standard normal distribution. Since a standard normal distribution is, wait for it, standard, then a lot of things are normalized to it or adjusted to it, and they use something called z-scores. We will see these z-scores later. These z-scores we will calculate later. We will compare later to critical z-scores. It'll come up a lot. So let's put in our z-score. What we want to do is we want to find the area between two ranges, essentially. So in other words, if we look at this, let's actually scroll. So if we look at this area, we want to put in this value and get this, but we don't want that area on the tail. We want between 2 areas. And so the way to do that is we're going to find one area of a high value and lower, and then subtract off one area of the low value and lower. In this case, we'll find the area of 1 standard deviation above the mean, which will be this thing right here. And then we will subtract off the area of 1 standard deviation below the mean or less, this area right here. And that will give us the range between the 2. So normal distribution, 1, 1 for cumulative, or if you want to just see, true also works. And then we'll subtract off the other one, negative 1, comma, I'm just going to put a 1. You see, it's just faster. You don't have to put it all in caps, true, but it's just nice. And then we get this value, which when we convert it to a nice percent, 68%. You note, of course, it's not exact. right? Rarely is, but 68%. That's pretty close. You see where that comes from. Same story. Norm for the next one for 2 standard deviations. NORM.S distribution. 2, 1 minus the other side of that. NORM.S distribution. I'm hitting the tab key. I'm hitting the arrow keys to select an option. Tab to essentially like have it complete, and then hit that that open parentheses. -2, 1, and we have 95%. It's not exactly. It turns out this is closer to 1.96. You see? But 2 is a reasonable approximation. Oops, hold on. There we go. Finally, 3 standard deviations. NORM.S distribution, 3, 1, minus NORM.S distribution. And I encourage you to do this because then it just improves your ability to manipulate Excel and just get you, any practice makes you more comfortable. Hit the tab, select A1 in this case, and then we have 99.7. That's the empirical rule. You can see where it comes from. Now you can memorize 68, 95, 99.7 just as a general skill set to have, and it's good to know it because that just a general estimate is really helpful. That said, knowing where it comes from also builds your intuition as to using these functions, this norm function, this NORM.DIST function. And because we built this up, we can do little things, like we can change this to 0.5 up here and minus 0.5. And now we see that there are 38% of observations within half a standard deviation of the mean. Or if you're really curious too, someone asked me this class, I was like, can we go even farther beyond 3? We absolutely can. We can put in NORM.S when we can do 4, 1 minus NORM.S distribution -4, 1. It's going to be a really high number, right? 99.99% of observations are within 4 standard deviations. But now that we know where this comes from, this empirical rule comes from, we can then find any number of other things. That's the essence of what I covered that unfortunately was lost. I can take a moment here since I got a couple moments. It goes pretty fast when there's no one here to talk to. I'm going to cover this again at the beginning of the next lecture, but just because it fits in so well, because I ran out of time in class. We can build a little bit more with NORM.INV, because NORM.INV has some interesting practical applications that are worth considering. And the big one is, the most straightforward one is warranties. So imagine you work at a company that makes kitchen appliances. Like all firms in this industry, you offer a warranty with your product. If it breaks within the warranty time frame, the company will replace it. But it's tricky determining how long a warranty should be. On one hand, you want the warranty to last a really long time because that's a better selling point. No one's going to want to buy a dishwasher that only lasts about, that the warranty expires after a month. It sends a bad signal about the quality of the dishwasher. At the same time, if you make the warranty last too long, it's very expensive because you're replacing more and more dishwashers. So if we can figure out a percent of dishwashers that we can replace, we can then establish when the warranty should be. And since we're going to assume that dishwasher life follows a normal distribution, we can use our NORM.INV function. So I'm going to use the data. I'm going to just use the examples from the notes. Let's imagine that dishwasher lasts an average of 10 years. And it has a standard deviation of 1.5 years. Now, I first need to talk to the accounting department and figure out how many dishwashers we can afford to replace. So let's imagine they say 4. So I'm just going to put in the, so 4% of dishwashers, right? If you want to throw in that percent, there we go, we can do that. So how long, I guess that technically is an X, this is the area. So I think it's called probability in the, what is it called, probability? Probability, percent, portion, however you want to put it. It's the same basic idea, there's 100%. And here we can only replace 4%. So in other words, we are thinking about this distribution. We'll recognize that some dishwashers are going to be really, really bad. Right? They will not last a long time, right? This is time, how long they last on this axis. Some of the dishwashers will be really, really good. Some will be, a lot will be average, but some will just by random chance, by how they're treated or how we treated them or something happened in shipping or maybe the construction or whatever it happened. And we don't know what, maybe the food they put in, who knows. Some of them just won't last very long. So we want to put in 4% here for these poor folks that had a bad dishwasher, and then we'll figure out what our warranty should be, how long they should last. So here we use norm invert, citing the probability. The mean or average is 10. The standard deviation is 1.5. And when we put this in, we get 7.37, roughly 7.37 years. Now, if we wanted to actually try to sell dishwashers, it would be weird if we say the warranty lasts 7.37 years. That looks strange. We're going to need to round to some appropriate number. The question is, should we round to 7 or should we round to like 7.5? 7.5 years could work, or 8 might work, but there's going to be a distinction as to which one we use, and I'll show you how that is with norm distribution. Let's type it in. So let's imagine we decide we are going to round up to 8. If we round up to 8, I want to know what percent of dishwashers we would actually replace. And we would replace not 9%, not 4%, but over 9%. This set it at 7.37, but we went higher to 8, so we are now getting a much larger area. And as a result, we've caused the company to lose money, right? We can't afford to replace 9. We can't afford to replace 9%. We can only afford to replace 4%. At most. We want the highest that, the highest warranty we can get, but not causing us to actually lose money on these dishwashers. So don't round up with this kind of value in this scenario. Always round down. And if we round down and we change that 8 to a 7, we get actually 2.3. We'll only replace 2.3. But 7 gives us a number. This number gives us something to work with. And maybe our marketing department finds out that no, people really, 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 really want the absolute most for their money. We can say, well, I guess we can do 7.25. They'll find that to be a really great selling point. We can still do that, but we could definitively tell them you can't do 7.5. 7.5 would be too many. And this gives us something to work with. Now let's go the other way. Now let's imagine that we're doing a sales, and we manage a bunch of salespeople, a sales team. and we want to offer a bonus to the best salesperson. If we set a threshold too high, then no one will get the bonus and they will resent you to set a goal that no one could achieve. But if we set it too low, then it will be too easy and people won't work any harder. Indeed, the workers that do work really hard will resent us for making it so easy that their lazy colleagues can be rewarded. So we want to be careful. So let's set our bonus at 40. So let's imagine that on average they make 40,000 in sales with a standard deviation of 5,000. And let's say that we want, see, it doesn't know what it's doing, that's okay. Let's say that we want to give 20% of our workforce a bonus. If we put 0.2 in, we find this is the result. Oops, not a percent, a dollar sign. 35. We want to give anyone who makes at least 35, maybe we'll round that to $36,000 in sales a bonus. But wait a minute, that's less than the average. Oh, we screwed up. You know what happened? We did this thing, and remember, this is what's always happening. We did 20%. That means we found the bottom 20%. If we wanted to say figure out whom we should fire, we fire the lowest 20% of workers, the worst performing 20%, then that would be the threshold that we choose to determine. But we want the 20% best. So again, we have to look at what area here would result in 20% over here, and that of course is 80, or 0.8. And here's our threshold of 44,208. Now, I have a similar problem with before. All right, because if I make it $44,208.11, that's like a really weird number to set as a threshold. It's not intuitive. If I round down, before that solved my problem because I was going away from the median, from the middle. But if I round down here, now I'm going toward the middle. And I want to go the other way. So I want to round up to 45,000. Again, if I do 44, mean of 40, standard deviation of 5,000, cumulative 1. You see, I'm actually, I'm not awarding the top 20%, I'm awarding the top 21.2%, which you could argue is close enough, but I mean, maybe it's not close enough. Maybe that was literally the most I could do was 20%. So I would want to round up. Let's make it 45 as the threshold. Granted, I'm not 20%, but I'm still pretty high. That's still going to get a lot of people. And hopefully give them the incentive that they need. Again, not hard, fast rules to deal with it. You just have to think intuitively. Should you round up or down? It depends. Are the lower values the issue or are higher values the issue? What side of the distribution you're working on? If lower values are the issue, if you're working over here, then you want to round down to get you farther away from the mean. If higher values are the issue, then you want to round up for the same reason, to get you farther away from the mean. So you have to think in terms of the context, you have to think in terms of what you're after.